Welcome back, everyone. We are in the week 7 problem solving session of the NPTEL course Control Engineering, and week 7 is about basics of control design. I am Teja Golla, a fifth year research scholar working under Santana Kapat at Embedded Power Management Lab, IIT Kharagpur. Let me share my screen. Can you see my screen? Yes, sir. Okay. Yeah, so we are in the week 7 problem solving session now, and week 7 is about control design. So we'll see what are the different types of control that we can use, like PI controller, PID controller, PID controller, and what will be the transfer function. But before that, we would like to see what will be the effect of adding poles or zeros to a closed loop transfer function and see how things will get changed. And also I have kept ready the MATLAB file so we can do more MATLAB simulation and visually see what will be the effect of these poles and zeros if we add them to closed loop transfer function, if we add them to open loop transfer function, and then see what are the changes. So rather than teaching it technically or theoretically, I would say, I thought it would be good if we have MATLAB simulation case studies and then see what will be the effect so that we can try a number of examples and then get an understanding how the poles and zeros are affecting that response. Basically, we'll check the step response. So I hope you can see my screen. So let me consider one system. So we have one system, and then let the system transfer function be g of s. And then we have say unity feedback. Okay. Say my input is r of s and my output is y of s. So now you know the closed loop transfer function can be given by y of s by r of s is equals to g of s by 1 plus g of s. This is what we have already studied. So now today what we are going to study is what will be the effect on the response overall system if I add say if I add one pole, say if I am adding 1 plus s by omega z, or if I'm adding one, sorry, if I'm adding one zero, or if I'm adding one pole, 1 plus s by omega b, how is it going to affect the response of the system? So which is what we are going to study now. So let us start with the effect of zero. Okay. So let me consider effect of zero. So here I'm considering effect of zero. So let us consider only that a zero has been added, and then I'm calling this as t of s. Okay. So my y of s by r of s, what will it be? It will be t of s into 1 plus s by omega z, right? So now if I simplify this, I'll get t of s plus 1 by omega z into s into t of s. So now you know that if my response of this is say c of t, in if I do inverse Laplace transform and then the time domain expression is c of t, then we know that s into t of s, it will be d by dt of c of t. This is what we have studied in the Laplace transform when we were discussing about the Laplace transform. So now my output can be written as, say if my output is y of t, I can get y of t is nothing but c of t plus 1 by omega z into d by dt of c of t. So this is my overall final expression that I will be getting by adding the zero. So now if you see, who is responsible for the additional term? The zero. So now by adding zero, we are getting this additional term. So this term is because of adding zero. Adding an additional zero. So if we are adding an additional zero, that is leading to this extra term 1 by omega z into d by dt of c of t. So what does this represent? So it is having a derivative effect of C of t. So it is like an extra term that is causing the derivative. So if my C of t is changing in the step format, then this is adding like an impulse. So this will try to fasten the response because it is having a derivative like what is a derivative effect. So this is acting like a predictive control, and it is predicting what is going to happen, and then it is adding that term to the existing C of t. So this will improve the step response and it will try to fasten the response, which is what we are going to see. So first I'll start with the effect of zero. So this is what we are getting. So let me consider one MATLAB example. So let me first explain what is there in this MATLAB code. So as I have mentioned in my earlier lecture, CLC is to clear this command window, and then clear is to clear the workspace, and then close all is to close if any figures are there. So this is just basic to clean up everything that is there in the command window as well as workspace. So we are not going to use the variables that we have defined in some other code. And then coming to the transfer function. So I'm considering three case studies. So the original transfer function is 1 by s square plus s plus 1. So which will have the imaginary poles. This is what I am considering. Now, sorry, this is for poles. So now let us shift to zeros. Yeah. So we are currently checking the effect of zeros on the closed loop transfer function. So let me just quickly summarize if you have missed. Okay, so what we were discussing is this week is about the control design. But before that, we wanted to know what will be the effect by adding zeros as well as poles to this closed loop transfer function. So here we have considered one closed loop transfer function with a forward blank transfer function of g of s. So the closed loop transfer function is g of s by 1 plus g of s. And we are checking what will be what will be the effect on the step response of this overall system if I'm adding in 0 to the overall closed loop transfer function, or if I'm adding a pole to the overall closed loop transfer function. So first we have started with the effect of zero. So I'm calling this g of s by 1 plus g of s as t of s. And then this will be t of s into 1 plus s by omega z. So now if I divide it into two terms, I can get one is t of s, one is s into t of s. If I do the inverse Laplace transform and consider this time domain response as c of t, then s into t of s will be the derivative, because we have discussed in the Laplace transform week that this will have a derivative effect. So this is called d by dt of c of t. Now this is the additional term, that is what we are getting from the additional zero. Now we are checking how this is going to affect the step response. So here we have g of n, which is what the original transfer function, original closed loop transfer function. Now we are trying to add one zero. So I'm placing a zero at what value? 1. And then now I'm be adding one additional zero, which will be placed at 20. So what I'm trying to do is I'm trying to place one zero at 1, which is close to imaginary axis. And then I'm trying to place one zero at 20, which is relatively further compared to the G2. So this is display of G1, G2, G3. So we can see the transfer function in the command window. Then how to get the step response. So there is one command called step command. So if you use this step command, then it will give the data. Y is the output response, T is the time response. So I'm calculating the step response of G1, step response G2, as well as step response of G3. So the data is stored in Y1 as well as T1, Y2 as well as T2, Y3 as well as T3. So now if we finally plot it, I'm considering one figure 1 where I'm plotting the step response of G1, G2, G3, and this is the command. And then these are the X labels as well as Y labels. And then I have also added legend so that we'll know which color corresponds to which of these cases. And then the last one is the title that I have added, which is the effect of adding zeros to the closed loop transfer function. So I have one original transfer function, which I'm considering as no zero. And then the second transfer function G2 corresponds to a 0 at 1. So this is 0 at s equal to minus 1. And the third one corresponds to 0 at s equals to 20. So if we add s equals to at minus 20. So this is what we are considering. So let us quickly run this and see what will be the effect. So if I quickly run this, here I'm getting the three transfer functions, and now I'll also get the plot. So let me maximize this. So this is the overall step response that we are getting. So if you see this one, no No zero means the original transfer function, which is in the blue color. And then the second one is the zero that we are adding at s equal to -1. So that is in this orange color. So as you can see, the derivative effect is trying to improve the response. It is kind of hastening the response. And in that sequence, it has caused one peak overshoot as well as the rise time has reduced. So it is trying to fasten the response because of the derivative effect. And then if I'm keeping the zero farther from the imaginary axis, then it is acting as if it doesn't have any effect on the response. It is matching with the original g of s. So from this example, what we are trying to see is what will be the effect if we are adding the zero. It is trying to improve the response. But if it is farther from the j omega axis, it is acting as if it doesn't have any effect. Saurabh, can you hear me? Yeah, good evening. Yeah, good evening, Saurabh. So I'll just quickly recap what you have missed so that you will also catch up with what I'm teaching. So in this week, we are discussing about adding poles as well as zeros to closed loop transfer function. We have started with this and we'll see how it is going to change the step response. So here I have considered one system and this is the closed loop transfer function. So I'm checking what will be the effect if I have one additional pole, if I have one additional zero. So I have started with the effect of zero. And if I'm calling this as T of S, then I will have two terms. One is T of S, one is S into T of S. So if my time domain of T of S is say C of T, then this will be derivative of C of T because of this S term, which we have studied in the earlier weeks while we are discussing transform, Laplace transform. So now my modified y of t will be C of t plus d by dt of C of t. So this additional term is coming because of the additional zero and it is having a derivative effect. So it is like it is predicting what will be happening and it is adding it to y of t. So it is kind of trying to fasten the response and then improve it. So this is what we'll get from the theoretical understanding. So I wanted to show you MATLAB example. So I have written one code. Again, these codes will be uploaded to the drive, so you can always access them. So I'll just quickly explain the code since you have missed. So we have the CLC clear and closure, which will clear the command window. So CLC will clear the command window. Let me put the video back here. Yeah. And clear will clear the workspace. So clear will clear the workspace. Then I am defining original transfer function, which I'm calling it as G1. And then to this, I am adding G2, two poles, one at omega equal s equal to -1, LHP zeros, sorry. I'm adding LHP zeros, one at s equal to -1 and one at s equals to -20. And then I'm checking the display will, it will display in the command window. And then I'm checking their step response. So there is a command called step, which will give the y data, amplitude data, as well as time data, which I'm storing in these variables for each of these transfer functions. And then I'm plotting this in figure 1. So this plot command are to plot it. I'll tell you why I have used a different style for the G3. And then I'm labeling X label, Y label, and then legend also I'm putting, and then title I have added. So let me just run it, which is what I was discussing. So if I'm adding a zero to the original transfer function, see, this is the blue color is the original one when there is no zero. And then if I'm adding a zero at s equals to -1, this is having a faster response, but that is causing to a little bit more overshoot. And then the rise time has reduced significantly because of the derivative effect. And if I'm placing a zero at s equals to -20, then it is more or less matching with the original transfer function as if the zero doesn't have any effect. So here the important aspect is if we are placing any zero close to the imaginary axis and we are talking about LHP zero, then it is trying to fasten the response. But if I'm keeping it farther away from the imaginary axis, then it is not having any effect. So this is what we have understood. So let me quickly write down. So is this clear? What we are trying to discuss here? Or do you have any confusion? So if I'm having a zero, which is closer to imaginary axis LHP, and then what is happening? This is trying to fasten the response because of the derivative effect, and this doesn't have any effect, doesn't have any effect. Why? Because it is farther away, it is farther. from the imaginary axis. So that is what we have understood from the response. So is this clear, Saurabh? So now let us see if I push it further. Okay, so I'm keeping it at 200 and then I'm checking. Yes, okay, so now I'm trying to push it further. Initially it was at 20. Now I'm pushing it to 200. So let me change this. So it is at 200. So let us run. So my response says it is perfectly matching. So the dot, that's why I have used dotted line so that we can see it is overlapping. So the last one, yellow color, is overlapping with the blue color, which is my original transfer function, saying that if I am adding 0, which is far away from the imaginary axis, it doesn't have any effect on the response. So now let us see if both the zeros are closer to the imaginary axis, what will be the effect? Here I have considered one closer to the imaginary, one farther away, far away. So let us consider one at 1, other one I am considering at 0.5. So I am considering at 0.5. So in the legend also I will change. So I'm considering at 1, I'm considering at 0.5. So now if you see, interesting thing, the zero point 0.5, which is relatively closer to the imaginary axis, is causing more overshoot because it is trying to uh, pull it faster because of the derivative effect. It is having that initial kick, so that's why it is trying to increase, but because of this it is causing overshoot. So that is responsible for this peak overshoot. So if I make it much closer to the imaginary axis, say instead of 0.5 I'm considering 0.1. So I'm considering one at -1, other one at zero point 0.1, and then if I run, now I am expected to see more overshoot. Let us see whether the, yes, so if you see, as it is closer to the imaginary axis, the overshoot is huge. So whenever a 0 is closer to the imaginary axis, it will have the more impact on the response, whereas if you push it away, then it will have less impact, and as you push it far away from the imaginary axis, it will not have any effect. So is this concept clear, how the 0 is affecting? Saurabh, is this clear? Yes, sir. Okay. So now let us see what will be the effect of RHP 0. So here we have considered LHP 0, right? So I'll quickly consider RHP 0. So I can copy paste. Yeah. So, yeah. So instead of plus, here I'll have minus. So instead of plus, here I'll have minus. Here also it will change. So I'm considering LHP 0. So because of this minus, I'll have one minus here and then also one minus. So now the derivative term is there, okay? But it is having a negative term. So instead of pulling it up, it will pull it down. So let us see what will be the response. So I'll consider two case studies. So we can use the same code. I'll use one is at +1, one is at -1. So I'll consider one RHP and one LHP. So let us change the legend also. So the second one is S equal to 1. The third one is S equal to, sorry, S equal to 1 plus 1. So let us see what will be the difference in the effect. So it is clear that the blue one is the original transfer function that we have. Now if we are adding a RHP 0, it is trying to pull down because the derivative term is getting subtracted. So it is pulling down in the opposite direction. So that's why, because of that, this dip is there. Whereas in the case of the top one, it is not having that dip because the derivative is trying to pull it up. So that's why it is reaching that one value faster, and because of that, this overshoot is there. Whereas in the case of RHP 0, it is having this dip at the beginning and it is eventually settling. Now let me consider the same case where I'm putting the RHP 0 far away from the imaginary axis. So I am putting it at 100. So S equals to 100. So here also S equals to plus 100. So let us run this and check what is the response. So the same thing, whether it is LHP or RHP 0, if it is far, far away from the imaginary axis, then it is not having any impact, because now I can see both are more or less overlapping very closely. The case where the 0 is not there, the case we are adding an RHP 0, but it is far away from the imaginary axis. So if I'm adding an LHP 0, it is trying to fasten the response, but because of that, there is an overshoot. Whereas in the case of RHP, it is pulling it down. So it is having a dip at the beginning because of the minus d by dt term. Whereas if I'm keeping the 0 far away from the imaginary axis, whether it is left hand side or right hand side, it is not having any impact on the response, and it is closely, perfectly, I mean, it is more or less matching with the original response. So this is the effect of 0 on the closed loop transfer function. Is this clear, Saurabh? If it is clear, we can go to the pole. So when they are closer to the imaginary axis, they are having an impact. As we push further, we are not having an impact. So in this way, we can see that if we are having any 0 that is affecting the response, our objective is to push it far away so that it will not have any impact. So this is the effect of zeros. Now coming to the effect of poles, and then we'll also be learning what are dominant poles. So similar to the previous example, I'll consider y of s by r of s is g of s by 1 plus g of s. And now I am having one pole, right? 1 by 1 plus s by omega p. Okay. So it is, say, I'm calling it as t of s. So we'll have t of s by 1 plus s by omega p. So let us, for the time being, assume that it is more or less something like this. Say s by omega p is more, so it is t of s by omega p. So it is nothing but omega p into t of s by s. So if I have the time domain of t of s is, say, c of t, then we know that t of s by s is nothing but integral of c of t dt, which we have learned from the Laplace domain. So basically, in the case of 0, it is having a derivative effect, whereas in the case of pole, it is having an integral effect. So basically, now the time domain will have an integral effect. So this will kind of slow down the response. We'll see. The derivative, what it will do, it will immediately respond, right? If there is any change in the c of t, the derivative will quickly change, and that will cause the output to change very quickly. Whereas in the case of integral, it has to integrate, so the change will be little bit slower. It will be little bit sluggish. It is slow, so it will change it very slowly. So the pole is having the integral effect, whereas the 0 is having the derivative effect. So this is the derivative effect because of the 0. And then if we add the pole, it will have the integral effect, and it will try to be sluggish. So it will try to be slow. It will slow down the response. Let us see. So is this concept clear, Saurabh?
Yes, sir.
Okay. So this is the code for effect of zeros on the closed loop transfer function. CL means closed loop, TF means transfer function. Now let us see the effect of the poles on the closed loop transfer function. So to start with, I'll consider two poles, LHP poles, because RHP pole is unstable. So we are considering only LHP poles as of now. So I'll consider one at 1, other one I'll consider at 10. And then same thing, step response, only the transfer function is changed, entire code is same. Here the, sorry, yeah, here the pole location is at is equal to -1, s equals to -10. This is the title, adding poles. Okay. So let us see, let us run it. So if I am running, the blue color is the original transfer function without any additional pole, whereas the orange one is the one which I am adding one pole at s equal to -1. And then the yellow color is the one where I'm adding the pole at s equals to -10. So in the case of 0, it is trying to fasten the response, because of that there is an overshoot and the rise time has reduced. In the case of pole, it is trying to have an integral effect which will slow down the response. And as you can see, the rise time has increased, or I should say deteriorated, because it is slowly reaching the 1. but because of this sluggish response or whatever integrator is trying to slow down, the overshoot has reduced. So because of this pole, the overshoot has reduced and it is becoming slow. And we are adding to the closed loop transfer function. So this is very important. If you are adding to open loop, that will have a different impact. If you are adding to the closed loop, that will have a different impact. We'll see the open loop later because closed loop is much easier to understand. So I have kept at s equals to -10 and it is more or less closely matching with the original given transfer function. So let me push it to 100. So I'm keeping it far away from the, so in my cursor is fast. Yeah. So if I'm keeping it s equals to -100, I'm considering one at, sorry, this has become 1000. So one at -1, one at -100. Yeah. So in this case, if you see the s equals to -100 case is matching with the original transfer function as if the pole doesn't have any effect. So similar to the zero, if the pole is far away from the imaginary axis, it will not have any impact, or I should say it will have negligible impact. So I have considered s equals to -1. I have considered s equals to -100, and I could say that if it is near to the imaginary axis, it will have an impact and it will slow down as well as it will reduce the overshoot. But if it is far away, it will not have any impact. So my next question is similar to the zero. What if I keep both close to the imaginary axis, but little bit different values? So I'm considering one at 1, the other one at 0.5. So both are close to imaginary axis, but one is closer, one is little bit far away. So this is my 0.5. So let us see what will be the effect. So if I'm placing closer to the imaginary axis, the more close it is, the slower it is, the response, right? The closer the pole is to the imaginary axis, the slower is the step response. So my blue color is the original response. Yellow color, orange color is at the pole at s equal to -1. Yellow color is s equal to -0.5. And if we are placing it closer to the imaginary axis, it has become slower. And similarly, the undershoot has, sorry, the overshoot has vanished. So if we are placing pole closer to the imaginary axis, the undershoot is reduced as well as the rise time has increased. So this is the effect of the pole on the closed loop transfer function. So the poles that are closer to the imaginary axis are having more effect on the transient response or the step response, and the poles that are far away from the imaginary axis are having negligible impact. So the poles that are closer to the imaginary axis are called dominant poles because they're having effect on the step response, whereas the ones which are far away are called non-dominant because they are not deciding any, are not having any impact on the step response. So these are called, the ones that are far away are called non-dominant poles, and the ones that are closer are called dominant poles. So these will affect the response. This will affect the transient response, and this will have negligible impact. So if we do not want some pole to be affecting the response, we'll try to push it far away from the omega axis, but on the LHP side. Let us quickly consider one example where I'll consider RHP pole because it is unstable, right? So let me consider the same pole. One is on the LHP, one is on the RHP. So one is at s equal to -1, one is at s equal to +1. And let us see what will happen. We know that it is unstable, but let us see. So if you see, the step response has gone to some very big value. It is in 10 to the power 24 because it is unstable and it is exponentially growing either in the positive side or negative side. It is exponentially growing. So we know that the system is unstable. Whereas if I, even if I keep it very large value, let us see again, we are keeping it 100 is equal to 100. Whether it is having negligible impact, it is still unstable. So in the case of zero, if we are keeping a pole far away from the imaginary axis, whether it is left hand side or right hand side, it will not have any impact. Whereas in the case of pole, it will have impact and the system is unstable. So we cannot keep anything on the right hand side if it comes to the pole. Yeah. So this is my original example. So s+2, s+1, and then this will be at -2. Yeah. So if it is far away, like the yellow color, it will have relatively lesser impact. Whereas if it is closer to the imaginary axis, it will have more impact. So that's all about the effect of poles on the closed loop transfer function. I hope the MATLAB simulation helped you to visualize how the effect is coming. If the concept is understood, then we'll go to the next topic, which is what will be the effect if we add poles to the open loop transfer function. So till now we have seen how it is going to affect if we add it to the closed loop transfer function. Now we'll see what will be the effect if we are going to add it to the open loop transfer function. So is the concept clear till now? What will be the effect of adding poles and zeros to closed loop transfer function? Can we move to this topic, Saurabh? Saurabh, is the concept clear? Okay. So now we are adding the poles to the open loop transfer function. So how are we going to see what will be the, now we are adding the poles to the open loop transfer function and we are interested in the closed loop transient response. We are interested in the closed loop transient response. Basically, what we are trying to do is we are trying to check the closed loop poles. So do you recollect any concept that we have learned which will correlate the open loop transfer function with the closed loop poles? Root locus, right? So if we are trying to plot the root locus of this, say, let us draw the transfer function log. So we have, say, g of s. With a gain k. So now the g of s is different in each of these cases. And then we are checking the closed loop poles. So we can plot the root locus of these transfer functions individually, and then we can see how the closed loop poles are getting affected. So for the initial case, 1 by s plus 2, since you have already studied, I'll just quickly draw the root locus. So if we have s plus 2, then the pole is at minus 2, and then the root locus will try to move in the direction of 0. So it will move in the left direction. It will move to the 0, that is at the infinite. And the first rule says that the root locus lies if the number of poles and zeros on the right hand side are odd. So on the right hand side of this root locus region, it is odd. So that's why the root locus exists in this region. Now, let us consider the other example. Yeah. Now let us consider the other example where I have pole at minus 2 and pole at minus 4. So pole at minus 2, pole at minus 4. Right? So the root locus exists only in this region, between the two poles. So both the poles will move towards each other and then they'll hit. And then we can say that when there are two poles, the asymptotes will be 90 degrees. So this will be the asymptote. So one will go to the top and one will go to the bottom. Is this clear, Saurabh? I'm just going a little faster because root locus is covered. So for the first
Yes, sir.
case, it is going to the 0, which is at infinite. The other case, it is colliding and then going. Now, if you have plus 2, plus 4, and plus 8, let us see how it is. We have 2, 4, 8. So the root locus lies between this region and then in this region. So this pole will go to infinite and then these two will collide and then move to the other two zeros. So in order to get that, we have to calculate the sigma. What is sigma? Summation of poles minus summation of zeros by number of poles minus number of zeros. So we'll get -8, -4, -2 by 3. So which is -14 by 3, close to -5, right? So the sigma is somewhere lying here. So the sigma is somewhere lying here. And if you calculate the asymptotes, you will get 60 degrees, 180 degrees, because there are three. So it is 180 into odd multiples by 3. So 60 into the odd multiple. So 60, then 180, and then 300. So if you draw the asymptotes will come something like this. Now, interestingly, these will collide and one will go in this direction and the other one will go in this direction. So at some point of time, they will hit the imaginary axis here or somewhere here. So now if I have a gain in the system and if I try to increase the gain, in this case as well as this case, the system is always stable. Even if I increase the gain, they are always on the LHP side. Whereas in this case, if I keep on increasing the gain, at some point of time, they will become unstable. So which is what we are getting from the root locus. So we can see that in which of these cases, I mean in all of these cases, by adding the pole, we are trying to shift the root locus. And in one of the cases, we can see that as the gain is increasing, the system is becoming unstable as well. I think the meeting might end quickly. If this ends, kindly come back so that we can again discuss the MATLAB plots related to this, how the step response is changing. But is the concept clear until this point?
No, sir.
Which one is not clear? Which part is not clear, Saurabh?
The last pointer.
Okay, this one, right? Yeah. So what I'm trying to
Yes,
tell
sir.
is,
Yes.
if we are trying to draw the root locus, we know on the x-axis, root locus lies in that region where on the right-hand side, the number of poles plus zero should be odd. So we know that between this -2 and -4, root locus exists, and then left to the -8, root locus exists. So the -8 will go to the infinite zero, so it will go in the left direction. Whereas this -2 and -4 will hit, and then it will move along the asymptotes, right? So in order to calculate the asymptotes, first I have calculated the centroid, which is the sigma. So the sigma is summation of poles minus summation of zeros by number of poles minus number of zeros. So my poles are at -2, -4, -8. So summation of that, and there are no zeros. So by number of poles. So it is more or less close to -5. So my sigma is at this point. And then if I am calculating the angle of the asymptotes, if I calculate the theta, then I'll get 180 degrees into 2n plus 1 by number of poles minus number of zeros. So this is 60 into 2n plus 1. So if I take n equals to 0, it is 60 degrees. If I take n equals to 1, then it will be 180 degrees. If I take n equals to 2, it will be 300 degrees. So the asymptotes will be one is at 60 degrees, one is at 300 degrees, or I can say -60 degrees. So the two poles that they will hit will move along these asymptotes. So now, given the angle of asymptotes, I can understand at some point of time they will hit the imaginary axis because they can't cross the they can't go above the asymptote. So at some point they'll hit the imaginary axis. Whereas in this case, they're going vertically up and down, so they'll not going to hit the imaginary axis. So for this case, at some point of time, say I have a gain in the system. Say I have a gain, say K. Okay. If I keep on increasing the gain K, then at some point of time, they're hitting the imaginary axis, which means the system is going unstable. So if I'm adding the pole to the open loop transfer function, I can see the root locus is changing or the poles are moving in different way depending upon how many poles are at what location I'm adding the poles. And in some of the cases, the system may become unstable as well. Here, the system is always stable. Here also, the system is always stable. But here, the system may become unstable depending upon the gain at which this is crossing the imaginary axis. Again, this K we can calculate using the Routh-Hurwitz criterion, which we have discussed in the earlier classes. So now for this example, we have seen that by adding the poles at different location, the response, the closed loop poles location can vary in a different manner depending upon the location of the poles, and system may become unstable. So that is the overall idea that we have discussed. Now we are going to see the response in the MATLAB. Is that clear, or some confusion is there still? Sorry.
No, sir. No.
Okay. So now let us go to the MATLAB. So this is the previous one which I'm closing. So I have discussed about the effect of poles as well as zero on the closed loop. Now I am talking about effect of poles on the open loop. Yeah. So this is the code that we are looking for. Again, I'll quickly explain. So these are clear as well as close all, which will clean the command window, workspace as well as the plots. And now I need open loop transfer function where I'm adding the poles, and then I want to check the step response of the closed loop transfer function. So this is my G1 open loop, G2 open loop, G3 open loop, and I'll display this so that I can see in the command window. And then for closed loop, I am considering say feedback gain of 1. Okay. Then it will calculate the closed loop transfer function, which is G1 open loop by 1 plus G1 open loop. So this the MATLAB will do, and this is a command. Once I get the closed loop transfer function, I am calculating the step response. Okay. So I'll tell you why I have added these gains. Okay. So I have done this, and then I'm plotting the figure, and this comment remains same. So now if I calculate the transfer functions, you can see that one is settling at one value, other one is settling at other value, this one is settling at some other value because I have given a step response. And if you can see, this has a DC gain, right? So the DC gain is not 1. So that's why it is not settling at 1. Similarly, the DC gain of this is not 1. So that's why it is not settling at 1. So let me do one thing. So what I mean to say is, I think I'll explain here. Say I have a transfer function G closed loop of S is 1 by S plus 3. So the DC gain is not 1. So that's why it will not settle at 1. So if the input is moving from 0 to 1, this guy will move from 0 to some other value. So I have to make something like this 1 by 1 plus S by 3, right? Which means I am multiplying this by 3. So the is 3 by S plus 3, right? So I have to multiply it by a factor so that the DC gain will become 1. So let us multiply that. So if I calculate all this, say if I'm running till this point, I have calculated. So now let us see the G1 closed loop. So what is my G1 closed loop? So if I do G1 closed loop, I think they are not calculated. Let us calculate this. Yeah. So if I calculate G1 closed loop, it is having 1 by S plus 3. So I have to multiply by 3 to make the DC gain 1. So this is just to adjust the DC gain so that the transfer function will settle at 1. So this has a DC gain of 9. DC gain means S equals to 0. So I'll multiply by 9 to basically make sure everything settles at 1. So if I calculate G3CL, it is having 65. So let us put that 65 gain. Okay. And then now the DC gain is 1. So all will be settling at 1. So as you can see, everything is settling at 1 because we have adjusted the DC gain. So now if you see the first case where there is no pole, and the second case where there is -1, means the closed loop. Oh, sorry. The legend has changed. So I think I will write like this: G1 of S. This will be G2 of S. And this will be G3 of, because now we are adding it to the open loop. We don't know how the closed loop will look like. So we do not know the locations. Yeah. So G1 of S, G2 of S, G3 of S. So in the G1 of S, it is 1 by S plus 2. This is 1 by S plus 2, S plus 4. This is 1 by S plus 2, S plus 4, S plus 8. And here we can see that the response has become sluggish, and then it has become a little bit slower. Now I would like to also, before increasing the gain, I'll also touch upon the root locus. Okay. So if you see the root locus, here we have seen in my earlier videos how to write the code, and then we have discussed. So if I start with 1 by S plus 2, I'm commenting this, and then I'll start with 1 by sirf s plus 2. So if I do this, how the root locus will look like. So let me plot it. It is running. So you can see it is moving from -2 to infinite, which is what we got. So even if we increase the gain, the system is always stable. So now if I do instead of s plus 2, if I have s plus 4 also, how the root locus will look like. So in this case, if you see, the poles are moving in the top and bottom direction, and everything is on the LHP side, so that the system will not never become unstable even if you increase the gain. Now let us do s plus 2 into s plus 4 into s plus 8. So which is what we have in the above line. So I can uncomment this. Now my G is s plus 2, s plus 4, s plus 8. Now here if you see, it is crossing the imaginary axis at certain point, as we have discussed. So it is crossing at this. Now, as I have said in my earlier videos, if you click at this point, right, so it will show the gain. So let me click at this point. So it is saying that at gain equals to 720, it is crossing the imaginary axis. So let us see. So is this root locus plot here? I have done the root locus to see what will be the gain at which it is crossing the imaginary axis. Is that clear?
Yes, sir.
Yeah. So now let us see. We'll remove the DC gain. Now we are not interested about the DC gain. So let us remove the DC gain for all, because we are not comparing the step response. Now we are checking whether the closed loop poles. So if we are increasing the gain, it is saying that the closed loop poles will cross the imaginary axis and it will go right hand side at gain of 720. So I'll give some gain less than 700 for all these three cases, and then see how my response is looking like. So I have given a gain of 700 because at 720 it is becoming unstable. So I have given a gain of 700. So now you can clearly see the yellow is becoming oscillatory because it is close to the imaginary axis. So that's why the oscillations are dying down, but there are oscillations. Whereas the other two cases, other two guys, the oscillations are not as much as this first guy, right? So the oscillations are very less. Whereas in the case of original case, the pole is moving on the left hand side. So it is always overdamped, right? This guy is overdamped because the root locus is going in this direction. Whereas this guy, it is complex conjugate. So that's why there are certain oscillations, but the oscillations are dying down, right? They have died down. But for the yellow case, the yellow case, the oscillations are more because they are closer to the imaginary axis, because they are coming closer to the imaginary axis. Here, they're always on the same vertical line. And now the gain is less than 720. So now let us consider a gain which is more. So let us consider a gain 900 or say 800. So now the third guy has to become unstable because the gain is 800. So this is 800. This also is 800. Let us run. So let us see. So as you can see, the third guy, he is exponentially increasing, right? So the gain has crossed that value. Now the poles are on the RHP side, closed loop poles. So that's why it has increased exponentially. And then if you can see on the amplitude, it is 10 to the power 22. So the gain is in it has reached that value that the system has become unstable. So let me delete this yellow color, and then let me delete this yellow color. So we can see the other two for the same gain. So if you see the other two, they are still stable for this high gain also, because the loops are the poles are on the LHP side. If you see the oscillations, they are same for the entire gain because they are on the same imaginary, I mean the same vertical line. So the real part is same and the imaginary part they are going towards the infinite. And then the first guy, for the same gain, it is still overdamped because the pole is on the left hand side. And this is the response of the first guy, which is 1 by s plus 2. So now, with this MATLAB simulation case study, what we have understood is by adding poles, sometimes the system may become unstable for a higher gain. But here we have considered one case where the first guy is overdamped and this guy is underdamped and this guy is also underdamped, but it can become unstable for certain gain, which we have obtained from root locus to see whether it is true or not. And then in all these three cases, we have tried operating at a lesser gain, and we have tried operating at gain such that this guy is becoming more oscillatory. And then we have also operated at that gain where this guy is unstable. And we have seen these two guys are always stable, whereas this guy has become unstable at certain gain. So in this way, we can see by adding the poles how the closed loop poles will vary, and then at what gain the system may become unstable. So this is the effect of adding poles to the open loop transfer function. Similarly, if we add zeros, then we can check how the root locus is changing, and then we can also do the same in the MATLAB and see how it is affecting. But by adding zero, things will get complicated. So I'm skipping that part, but we can do the same exercise. Now we'll go to the design aspect and the controller, how to design. So that's why I have not covered that concept so that I can cover other important concepts. So till now we have discussed the effect of adding poles and zeros to the closed loop transfer function, as well as effect of adding poles to the open loop transfer function. So is this concept clear, Saurabh? Okay. So if the concept is clear, let us move to another important concept, which is the P control, PD control, as well as PID control. So I have given one open loop unstable transfer function, and you can see, Saurabh, the concept is clear, right? Huh. So now let us move to another important topic, which is P control, PD control, as well as PID control. So what will be the impact if you use proportional control? What will be the impact if you use PD control? What will be the impact if you do PID control? So I have given one open loop unstable plant transfer function, and I have given three cases. In the first case, we are using proportional control with gain Kp, and we are asking whether it can stabilize for any value of Kp. Can it be stabilized? So that is the question. Then we'll see, and then we'll move to PD control. And if it has gains Kp, Kd, whether it can stabilize the system, also whether the system can achieve zero steady state error, whether it is possible or not. In the third case, we have PID control, and the gains are Kp, Ka, as well as Kd. And then we are asking whether the system can stabilize and also whether it can achieve zero steady state error. So this is the question that I have given. Is the question clear, first of all? Saurabh, is the question clear?
No, sir. Sir, repeat again.
Okay, okay. Let me just draw so that I think it will be clear. So let me draw the closed loop diagram. So I have a plant transformation G. So I have this is controller transfer function GC of S. This is the plant transfer function G of S. So I have a closed loop system. Yeah. So this is my R of S. This is my Y of S. So this G of S is given here. So this G of S is given here. And we know that this is unstable based on the poles, because one pole is on the LHP, one pole is on the RHP. So we can say from here, S is equals to plus or minus square root of B, B is some value. So this is unstable because there is one RHP pole. So now I am considering P control, PD control, and PID control. And then I'm asking whether the system can be stabilized, also whether the zero steady state error can be obtained or not. So this is the question. And now we have to see each one. Say if it is P control, if it is P control, if it is PD control, if it is PID control, we'll have to see what will be the transfer function looking like. So in this case, GC of S will be just a gain Kp. In this case, GC of S will be Kp plus Kd into S because P and derivative. In this case, it will be Kp plus Ki by S plus Kd into S. So we have to see for each of these cases whether the system can be stabilized, which means when we are talking about overall system, we are asking whether the closed loop poles are on the LHP or not. With P control, PD control, PID control, also we need zero steady state error for step response. as well as stability. So we are checking the stability, and this is again step response. Is the question clear, Saurabh, now?
Yes, sir. Yes, sir.
Yeah. So we, for all the three cases, first of all, let us find the y of s by r of s. So y of s by r of s is equals to gc of s into g of s by 1 plus gc of s into g of s. So we'll start with the proportional gain, and then we'll go to PD control as well as PID control. So in the first case, we have asked whether the proportional gain Kp can stabilize the system. So let us start with A. So I'm starting with A. So in the case of A, my GC of S is just Kp. So let us calculate y of s by r of s. So we can calculate y of s by r of s is equals to Kp into 1 by s square minus b by 1 plus Kp by s square minus b. So it is Kp by s square plus Kp minus b. So can the system be stabilized by choosing certain value of Kp, or is it unstable, or can you comment on the poles? Saurabh? So this is my closed loop transfer function, right? So can this be stabilized, or what do you think? By choosing certain value of Kp, what can we do? So the question is whether it can be stabilized. So the open loop is unstable because there is a pole in the RHP. Now this is my closed loop transfer function. This is the characteristic equation. So I'm asking for any value of Kp, can we stabilize the system? Not mean for certain value of Kp, can we stabilize the system? Is there any such condition?
The system is unstable.
Why is it? Why? How are you saying that? So the characteristic equation is this, right? S square plus Kp minus b is equals to 0. So we have to find the poles of this, and then we have to comment on the stability. So if I consider Kp minus b is greater than 0, then my poles are what? S is equals to plus or minus j into square root of Kp minus b. So the poles, closed loop poles, are basically on the imaginary axis. Imaginary axis. So the system is marginally stable. Is that clear? You are getting right. If I consider Kp minus b is greater than 0, say it is a positive number 9. So s square plus 9 equals to 0. So s will be plus or minus j3, which means it is on the imaginary axis. So the system is marginally stable, not fully stable. Because the maximum I can do is bring the poles on the imaginary axis. If my Kp is less than b, then it is unstable. So the maximum I can do is to bring them on the imaginary axis, but not on the left hand side if I have only Kp. Is that clear, Saurabh? So if I'm using only proportional gain, the maximum I can do is bring the poles, closed loop poles on the imaginary axis, not on the left hand side. So that is the limitation. Clear or any confusion? Okay. Yes. Yes, sir. Okay. So now the question is whether the proportional gain can stabilize the system. No, the maximum it can do is marginally stable, not fully stable. So now the second question, whether the PD control can stabilize the system, let us see. And also whether the system can achieve zero steady state error for step response. Okay, let us see. So in the case of B, I have my, in the case of B, I have my GC of S is equals to Kp plus Kd into S because it is a PD control. So now in this case, let us calculate the y of S by R of S, right? Yeah, closed loop transfer function. Let us calculate y of S by R of S. So now this will be GC Kp plus KDS into plant transfer function 1 by S square minus B by Kp plus KDS into 1 by S square minus B plus 1, right? So if I calculate this, it will be Kp plus KD into S in the numerator. My denominator has S square plus KDS plus Kp minus B. Yeah. So this is my closed loop poles. So now can I stabilize the system?
Yes, sir.
Yes, right? Very good. So now if I consider my KD to be positive, also Kp minus B to be positive, then I'll have poles on the LHP. LHP. So now with this, I can say that I can stabilize the system. The system can be stabilized. So if you use only a proportional control, the maximum you can do is to bring the poles on the imaginary axis. Whereas in this case, the poles can be brought to LHP and then the system can be stabilized for certain values of KD and KP. So for KD greater than 0 as well as KP minus B greater than 0, the system can be stabilized. So the answer for the first part of B, whether the PD control can stabilize the system, yes. Now we have to see whether the system can achieve zero steady state error for step response. So we know for step response, R of S is 1 by S, so we can calculate Y of S. Yeah. So my Y of S is KP plus KDS by S square plus KDS into plus Kp minus B. So now for step response, I can calculate for step response, we can calculate Y of S is R of S into this. So R of S is 1 by S and this is Kp plus Kd into S by S square plus KdS plus Kp minus B. So we are asking the zero steady state error. So if we are asking zero steady state error, ES of T, then we know final value theorem, S tending to 0, S into Y of S. So S and S will get cancelled. So we'll get limit S tends to 0, Kp plus Kd into S by S square plus KdS plus Kp minus B. So if you substitute 0, then we'll get Kp by Kp minus B. So can this be made 0? Can the steady state error be made 0? Again, you have to consider this case also. The system is stabilized, which means KD is greater than 0 and KP minus B is greater than 0. So given this condition, can the steady state error be 0? The steady state error can be made 0 when KP equals to 0, but KP can't be 0. So can the steady state error be 0?
No, sir. The system cannot achieve a zero state error.
Yes, very good, because it is Kp by Kp minus B and Kp is a positive number greater than B, so it can never become 0. However, I can increase the Kp. So if I consider Kp to be very, very high, then I can get error steady state to be closer to 1, but it can never be 0. So in this case, I can say that the zero steady state error is not possible. So this zero steady state error is not possible. Now let us go back.
Yes, sir.
Whether the PD control can stabilize, yes, but whether the system can achieve zero steady state, no. So now if you see whether a PID control can stabilize the system and whether it can achieve zero steady state error, let us see. So for PID controller, again we'll write the transfer function and then let us start solving. So the PID controller, we have GC of S is equals to Kp plus Ki by S plus Kd into S. So now my Y of S by R of S will be this Kp GC is Kd S square plus Kps plus Ki by S into the plant transfer function 1 by S square minus B by 1 plus Kd S square plus Kps plus ki by s into s square minus b. So if you simplify this, we'll get on the numerator, we'll have kd into s square plus kp into s plus ki divided by s cube plus kd s square plus kp minus b into s plus ki. So can the system be stabilized in this case?
Yes, sir. The PID controller can stabilize, sir.
Yes, very good. By considering kd to be greater than 0, kp minus b greater than 0, first of all, and then if you do Routh-Hurwitz criteria, you will get a condition to stabilize the system. So the system can be stabilized. If you do Routh-Hurwitz, you will get the condition system can be stabilized because all the coefficients are there. Now I have to calculate error steady state t tending to infinite, which means it is limit s tending to 0, s into y of s is nothing but y of s by r of s into r of s, which is 1 by s. Right? So these two will get cancelled. Similarly, like the previous case, so we'll get limit s tends to 0 y of s by r of s. So we'll have limit s tends to 0. What is this? Kd into s square plus kp into s plus ki by. Actually, this is not error. I think I have. This is y steady state. So this is not error. Actually, this is y steady state. Error is input minus y steady state. So I think I have made a mistake. My bad. So this is y steady state. So in this previous case, my actually output should be 1, right? If I am giving step response, output should be close to 1. So this is 0, but I need 1. This cannot become 1, right? So actually my steady state output should reach 1, then the error is 0. But if I increase kp, if I consider very high kp, then it can be close to 1, but never equal to 1. So that is not possible. So 0 steady state error is not possible. So error steady state can't be 0. Because basically I'm calculating y of t. So r of t minus y of t is error. So if y of t is 1, r of t minus y of t is 0. But here it is close to 1, not exactly 1. It is lesser than 1. So there is some finite steady state. Now let us calculate in this case. It is denominator is s cube plus kd into s square plus kp minus b into s plus ki. So in this case, if you substitute s equals to 0, you will get ki by ki, which means equals to 1. So my y is becoming 1. So now the error is nothing but error steady state at t tending to infinity is r of t, which is step function, minus y steady state of t, which means it is becoming 0. So yes, this can be achieve zero steady state error. Is this clear, Saurabh?
Yes, sir. The system zero state error.
Yes, zero steady state error. Also, it can be stabilized. So if we quickly
Yes, sir.
summarize, so depending upon our requirement, we have to choose the control. So sometimes the control that we are choosing may not be sufficient. Sometimes it needs some additional term in the control so that it can be achieved. So we can see that if you use P control, the maximum you can do is marginally stable, but you cannot have LHP poles, closed loop poles. Whereas in the case of second case, we can stabilize the system, but it will have non-zero steady state error. Whereas in the case of PID controller, we can stabilize, and then we can achieve zero steady state error. Which means if my objective is to stabilize the given unstable transfer open loop transfer function, and if I want to achieve zero steady state error, For a step response, then I need to have PID control. P control is not sufficient to first even stabilize the system. PD control can stabilize, but it cannot achieve non-zero steady state error, whereas PID controller can achieve both zero steady state error, also it can stabilize the system. So given the requirement, we might have to choose a control. So now, if you ask me whether PID control can achieve zero steady state error for ramp response, we have to see. If it is not sufficient, then we have to increase the order of the controller to achieve that zero steady state error for ramp response. So depending upon our requirement, this can vary.
Yes, sir.
So this example is clear. Saurabh?
Yes.
Okay. So if this is clear,
Yes, sir.
yeah. So similarly, we can do this GC into this whatever transfer function, and then we can do MATLAB also. So let me see whether I can do that because we have this feedback, right? So let us consider effect of zero. I'll consider this as problem one. Hyphen we cannot use. So I think I'll write it as PID control. So this is my code. Uh, Let us open this code. So this is my given transfer function. So I'll consider my G as s square minus 9. So this is my initial transfer function G1. Now I'm writing GC, G underscore C. So first let me do P control. So if I'm doing P control, I can only choose GC to be a constant, and my math says that constant has to be greater than B. So I'll consider GC to be say 16. I can consider 16 or 10, whatever. I'm considering 16. And then what I'll do is I'll calculate the closed loop transfer function. So how can I calculate the closed loop transfer function? I can get this comment from here where I have used this feedback, right? So I will use this, and then here I can get my G1 closed loop 1. So G1 closed loop 1 is nothing but feedback of G1 star GC, because I'm multiplying G1 into GC, and then feedback gain is 1. Is this clear how we have written for P control? Saurabh?
Yes, sir.
So now I'll remove all this, and then we can do for PD control as well as PID control. So PD control GC, it has to be what? S square KD should be greater than 0 and KP should be greater than B. So KP I'm considering 16 plus KD should be positive. So I'll consider 2 star S. So my GC is now 16 into 2S. So let me consider this as GC1. So I can call this as GC1, and let me consider this as GC2. So I can call this as GC2. Now this is second case, so I'm considering this G1 closed loop 2. So now this is also done. Now let me go to the PID control. So if I go to PID control, I'm calling it as GC3. So KP plus KD plus KI by S. So let us consider, we have to see the condition from Routh-Hurwitz criteria if there is any interrelation. But let me consider KI to be 1, and then let us see what will be the closed loop poles, or we might be making a mistake. Again, we have to see that. Then feedback will be G1 into GC3, and then this will be G1 3. So if we run it, let us see what we are getting. Yeah. So if we are running, the first one is G1 closed loop of L, which is 16 by S square plus 7, which means this is marginally stable, right? For the proportional case. Saurabh, did you get the code or should I explain it again?
Sir, repeat again, sir.
Yeah,
Sorry.
yeah. Yeah, so I am this clear command is common for all the codes. First, I have defined the transfer function. So in my problem, I have considered s square minus b. So maybe I can consider here, define the transfer function, and I have considered b to be equal to 6, b equal to 9. So I have considered my b to be 9. So again, the meeting might end in a minute. Once the meeting ends, kindly come back so we can discuss more on this. So I have considered b to be 9 because it has to be set a number for the MATLAB to compute. So I have considered g1 to be 1 by s square minus 9. So based on our result, I have considered p control, pd control as well as pid control. And in the case of p control, my g closed loop is kp, right? And kp has to be greater than b. So I have considered kp to be 16. And then my feedback is what? Forward path and then this one. So forward path is G1 into GC1. If I go back, it is GC into G. So that is my forward path and then feedback gain is 1. So that's why. And this command will give me G1 into GC1 by 1 plus G1 into GC1. Okay, so until P control it is clear, right? Saurabh?
Yes, sir.
Now coming to PD control, in order to stabilize, I got one condition Kp should be greater than B, which means Kp should be greater than 9 and Kd should be positive. And my transfer function is Kp plus Kd into S. So I have considered Kp to be 16, which is greater than 9 and Kd should be positive. So I have considered 2. So my transfer function is 16 plus 2 into S and the closed loop transfer function is G1 into GC2 where GC2 is my PD control. This will give me G1 into G closed loop. That is for the PD control. Is that clear? Saurabh? Okay. Now coming to the last case, I have to solve Routh-Hurwitz criterion to get all the conditions that will stabilize the system. But from this, I can get all the coefficients are positive. So KD is positive, KP minus B is positive, and KI is also positive. So I have taken one guess value of KI to be 1. This is KP plus KD into S plus KI by S. And then I have tried to solve. And then I will see whether I am getting the transfer function or not. So if I display it, I have to display first the ZPK of G1 underscore closed loop 1. Okay. And then I'll repeat the same for all the other transfer functions. Okay. So let me copy this and then paste. Then this will be 2. Then paste. This will be 3. So if you run it, let us quickly run the MATLAB code and then check what is happening. Yeah. So in the case of first case, which is Z1 closed loop 1, we are getting 16 by S square plus 7. So maximum we can do is marginally stabilize the system, not fully stable. In the case of second, sorry, 2 into S plus 8 by S square plus 2S plus 7, it is stabilized. But we have seen the step response. It cannot achieve zero steady state error. Again, you can give step response and then check how the step response is changing, whether it is reaching or not. But I'm not going into those details because we have to cover the other concepts as well. And then for the third case, where we have used the PID control, we have obtained the system is stable because I can see this is on the LHP side. Similarly, this is also on the LHP side. So we can say the system is stable. But for this case, we can also say the zero steady state error can be achieved. Again, you can give the step response and see whether we are able to achieve the zero steady state error or not. But here we are not doing that. You can actually consider the other code and write the step response and then see whether it is achieving the step response and with zero steady state error or not. But for the time being, I'm not covering that, but you can consider this as an example and then write the code for the step response, which is there in the other MATLAB files and check for yourself. So is the MATLAB code clear, Saurabh?
Yes, sir.
So now with this, we have discussed about the PID control, but we can also discuss about lead lag compensation, which is also like widely used in the control systems application. So what is lead control? What is lag? I mean, what is lead compensation? What is lag compensation? And what is leading and what is lagging? So basically, when we say lag, it means we are talking about the phase. Okay, so we can generalize the transfer function as GC of S is equals to K into S plus 1 0 and 1 pole. So it has some DC constant, DC gain multiplied by S plus Z and divided by S plus P. So whether the 0 is bigger, again, both are LHP, whether the 0 is bigger or the pole is bigger, that will define the lead or lag. Say if my 0 is smaller, if my 0 is smaller, sorry, if my pole is smaller and 0 is far away. So this is lag compensation. Then we'll come back again. We have seen that if 0 is far away, then it will not have any impact, right? So in the same case, if we have 0 to be greater than P, and then say pole is very small, pole is very close to the origin. So then we can say that K into S plus Z by S plus P. Say pole is very small, I can consider this as K into S plus Z by S. So now we will get K plus Kz by S. So this can be written as Kp plus Ki by S, right? So we are basically getting a PI control, but instead of pole at 0, we are having pole that is on the LHP side. So if my transfer function looks like GC of S, which is equals to K into S plus Z by S plus P, then what are we getting? We are getting something like a PI control. Because if we approximate the denominator to be S, then we are getting in a PI control. But for the lag compensation, the transfer function is K into S plus Z by S plus P, which means the 0 is coming before then the pole. And again, sorry, the pole is coming before 0. The magnitude of the pole is smaller and the magnitude of the 0 is little bit larger. Sorry for confusion. Yeah. So is this clear, Saurabh, the concept?
Yes, sir.
Yeah. So now if I take the things common, like if I write it in this way, I can write K into Z by P into 1 plus S by Z and 1 plus S by P. So this is the normalized transfer function I can write. So let us take that. So GC of S is equals to K into Z by P into 1 plus S by Z into 1 plus S by P. So we can get the DC gain from this, which is mod of GC j omega at omega equals to 0. We can get the gain is nothing but K into Z by P. So now if we draw the border plot, which we have learned in the earlier last class. So let us draw the border plot. So if I calculate the so we know the pole will come first, not the 0. So the pole will come first. Say the pole is here and then the 0 is here. So this is my pole, this is my 0. Initially, it has a constant uh, magnitude of kz by p. So if we are writing in the magnitude, it will have 20 log k. So if I use orange color to draw, so it will have 20 log k until the pole. After the pole, it will fall with minus 20 dB per decade, and then again it will become constant. So at the beginning, we have 20 log kz by p And since the pole has come first it will start dropping with minus 20 dB per decade. And once the zero comes, then it will have plus 20 dB per decade, which will cancel out the minus 20 and it will become constant. So this is the magnitude plot. So mod Gj omega. And then this is omega. Is the magnitude plot clear?
Yes, sir.
So now similarly, if we draw the phase, so let me draw the phase plot. Phase will start from zero because at s equals to zero, I mean omega equals to zero, phase is zero. So it will start from omega equals to zero. It will start from zero. So this is my omega. This is my phase. So this is my phase angle Gj omega. So this is my pole and this is my zero. Yeah. So what will happen is, say pole and zero are not too far, but say relatively closer. Then it will initially start with minus 10. I mean, it will initially start with 0 degrees. And then once we know at the pole, it should hit 45 degrees. So it will hit 45 degrees at the pole. This we have studied last time. And then 10 times the pole, say 10 times the pole is here. This is 10p. There it will hit 90 degrees. So there it should hit minus 90 degrees. But say it is relatively far. So now after this time, it will, so I think it will fall something like this. Right? And then this is 1 0 and then one pole, right? So effectively both will cancel out and then effectively the phase will come back to zero at infinite. But because of the pole, it is falling down and then because of the zero, it will level down. So it will go something like this. Are you getting this point? Pole will contribute 90 degrees and zero will contribute, pole will contribute minus 90 and then zero will contribute plus 90 and then both will get cancelled out. But because pole is coming first this will dip and then once it is done, then omega will try to increase. So we can say that something, it will first, sorry, so it will initially start to fall and then at one point it will increase and then it will come back to zero because at omega equal to infinite, we'll again get the angle to be zero. So basically because of the pole, it will dip first and then because of the zero, again, it will start to increase.
Yes, sir. Okay.
Because this is contributing minus 90 degrees and then this will contribute plus 90 degrees. Or to make it clear, I can draw the pole is starting from zero, then it will go to, sorry, minus 90 degrees and then it will settle at minus 90 and then the zero will start dotted line. Can I draw dotted line? Okay. That. Okay. We'll have wherever the pole is there, then we'll try to increase to 90 degrees. And then it will settle. So basically, we are saying this is 0 degrees, this is minus 90 degrees, and this is plus 90 degrees. So we are trying to add up. So there will be a dip and then again there will be an increase. So because of this, it will decrease. And once this slope is gone, then this will pick up. So eventually, how we are going to get, it will start something at zero, it will dip, and then once it will come, and then it will settle at zero. So that's how we are getting. So because of the pole, it will dip first, and then after zero, it will pick up. Clear, right? Any
Yes, sir.
confusion? Okay. So
No,
this
sir.
is Yeah. So this is PI control. Now coming to lead compensation. One more point. Again, phase is lagging, right? So if you see, phase is always below 0 degrees. So that's why it is called lag compensation, because we are adding phase lag. So this is phase lag. So that's why it is lag compensation, because it is having phase lag. Similarly, if you consider to compare lead compensation, it is PD control, just the opposite. And again, it has phase lead. So if I draw the transfer function, GC of S is K into S plus Z by S plus P. Here it is leading means 0 should come first. So the magnitude of 0 will be lesser than pole, just the opposite. So if you calculate this, it is K into Z by P into 1 plus S by Z by 1 plus S by P. Here 0 is small, right? So numerator I can consider as S only, right? 0 is much, much smaller. So we can consider it as KPD, right? So we can consider this as KP plus KI by S. So it is something like KPS plus KI by S. But here, if it is sorry, my bad, this is the opposite. Sorry. KP plus KD into S. So we can get it as something KP into S plus KD into S plus KP by KD. And then if we consider some pole, then it is like KD into S plus some KP by KD by some pole S plus P. In the original case, the derivative, there is no pole, right? But in actual life, we cannot implement this KDS because this is non-causal, right? So we cannot implement this. This is non-causal. So we need to have a filter. So what we do is we consider something like this. Kp plus Kd into S by some filter, tau S plus 1. So this is now causal because this is also improper transfer function. This is improper transfer function. So we cannot implement. Whereas this is proper transfer function. So we can implement. So now if you simplify this, you will get Kp into T plus Kd into S plus 1 by tau into S plus 1. So it is in this K into S plus Z by S plus P. So this is basically representing the PD control if my 0 is coming first. So now let us draw the same Bode plot and let us quickly compare. So this is mod G and then this is omega. So in this case, 0 is coming first. Say 0 is here and then 4 is here. So in such case, let me do this. So why I'm pulling down, I'll explain. Initially, it will start with a constant value, which is 20 log kz by p, same. Then once it hits 0, it will start increasing, and then once it will hit 4, it will be constant. So this is 20 log kz by p, and then this is plus 20 dB per decade. Now if you go to phase, This is the angle GJ omega. So there is a 0 here, and then there is a pole here. So if you draw with a thin line, starting with 0, so the phase will go from 0. So the phase will start at 0, and then it will go to 90 degrees. So this is 90, and then it will settle at 90. In the case of pole, it will start from 0 and then go here till here, or maybe somewhere before. It will go till before, and then it will start falling, and then it goes minus 90 degrees, and then it stays there. So basically, this is plus 90 degrees. This is minus 90 degrees. So we are trying to add those. So initially it will start, and then it will increase. And then once the effect of pole comes, it is more or less constant. And then once the zero effect is there, now it will fall down, and then it will come back. So this is 0 degrees. This is 0 degrees. So in between, there will be a peak. Okay, now if you see, this is phase lead. Phase is always positive. So that is phase lead. So that's why it is called lead compensation. So the concept is very clear. If the pole is coming first, then there will be phase dip, and then it will increase. If the 0 is coming first, there will be phase increment, and then it will start decreasing. And that's why we are calling this lag compensation because of the phase lag. And then we are calling this lead compensation because of the phase lead. So here we'll have a minima, phase minima. So if I use this, so here we'll have phase minima. Here we'll have phase maxima, which is always in between 0 and 4. This is phase maximum. Is this clear, Saurabh? What are lead and lag compensation? So lag is nothing but clear, right?
Sir, basic difference between lead and lag compensator, sir?
So when I have a closed loop system, say I have a closed loop system, something like this, and then I want to add a phase to the plant. If I want phase addition, it is like phase leading. So I'll use lead compensation. If I have to reduce the phase, then I have to lag the phase, which means lag compensation. So both uh, in this transfer function wise, both are same. But if we want lag compensation, pole should come before, and it acts like a PI control. In the case of lead compensation, 0 will come before, and it acts like a PD control. So basically, one is PI control, one is PD control, but it is not exactly PI PD. So that's why they have given a different name. One is lead, one is lag. So lead is what? It will add phase to the system. Lag is something that will reduce the phase in the system. So depending upon my requirement, if I need lead or if I need lag, accordingly I'll choose lead or lag compensation, and then my poles at 0 locations will be fixed. So how this is going to affect, that will be one interesting case study, which I'll discuss when this design using root locus as well as design using frequency are there in the upcoming weeks. There we can consider one example and then see how the lead is affecting the system, how the lag is affecting the system. It will be interesting. So one is basically to reduce the phase, one is to basically increase the phase.
Oh, yes, sir. Thank you.
So now this is the final topic. Let us quickly go to MATLAB. I have also considered one MATLAB code for the same. So again, initially it is same, clearing the command window as well as the workspace. Then I have defined a transfer function. Okay. So G1 is something, some k into s plus z, s plus p. So G2 is some k into s plus, what do you call? Sorry, s plus z by s plus p. So in the first case, 0 is coming first or pole is coming first?
0.
0 is coming first, right? So I can say z is less than p. So if 0 is coming first, first phase will increase, then it will decrease. So is it lead or lag compensation?
So lead.
Lead, very good. So this is lead compensation. So what is the other example? Z is greater than P or smaller than P?
Sir, it's smaller than P.
Yeah, so P is basically smaller than Z because pole is at 5 minus 5 and 0 is at minus 20. So pole is lesser than 0. So the pole will have the impact first. So first it will try to decrease and then the phase will increase. So is this lead or lag compensation?
So it's a lead.
This is lag, right? First
Like
lag.
lag. Sir.
So it is lag. So I have two transfer functions. One is lead, one is lag, and then I'm plotting. Sorry. So this is the Bode plot options, and first I'm plotting the lead compensator in figure one. Then I'm plotting the lag compensator in the figure two. Yeah. So let us run. It is running. Okay. So first I'm considering figure one. So if you see in the figure one, it is having lead. So my first transfer function is lead. And then the figure 2, sorry, this is figure 2. Figure 2 phase is below 0. So that's why it is having phase lag. So that's why it is lag compensation. But now if you see here, I have considered G1 to have some gain 50. So instead of 50, say I have considered 100. And then instead of 0.25, I will consider say 10. Okay, and then I'll plot it and then I'll keep those plots. I'll not close them. So let us see what will happen. Oh, I can't use two different colors. Huh? I think hold on is missing. Just a minute. Hold on. Hold on. Here also use hold on. Okay. So initially I have started with a lesser gain 50 and then here I have started with 1. Okay, so initially I started with lesser gain and then I have obtained the plots. Now what I'm doing is I am increasing the gain to 100. Here I am increasing the gain to 10. And then I am not closing the plots. So I wanted to see two cases. Let me see. Yeah. So I have increased the gain, right? So the blue color is the first case. And then the second case is the orange color. If you see here, orange color is there, right? Let me first remove this. Uh, I use the orange. I use line style to be dash. So if you see, sorry, the phase remains same. If I am increasing the gain, what will happen? The plot will move up, but the phase remains same. In both the cases, phase will remain same, but using K, I can shift the magnitude plot up or down. So if I need phase lag, then I'll use lag compensation. But if I need gain to be above or below, then I can play with the K. So either I can shift the magnitude plot above or I can shift the magnitude plot below. Similarly, in the case of the figure 2, this is a lag compensation. But if you see, the gain is higher in the second case. So the orange is above, but the lag is same for the phase plot is same for both. So if I use line style to be dash, I think phase is going below probably. That's why we are not able to see. I think. uh, So I think now this makes more sense. So if you see, the phase remains same in both the cases, but depending upon the gain K, either it will shift above or it will shift below. So now what I wanted to say is, in the case of lead compensation, lag compensation, how are we going to choose? So I have one system and then I want to have the border plot in such a way that it will have I want to reduce the phase of the system and I want to pull it above. I want the border plot to be shifted above. So if I need lag compensation, I'll choose the lag compensation and then I'll place the Z and P in such a way how much phase lag I need. But if I want to pull it above, I will multiply the gain K so that it will go from this border plot to this border plot. So I can use the gain K to either shift it above or shift it below, and I can use the phase to either lead or lag based on the lead compensation, lag compensation. If pole comes before zero, lag compensation. If zero comes before pole, it is lead compensation. So this is the basic difference between lead and lag compensation. Any doubts in this?
Yes, sir. No, sir.
So similarly, if you reduce it, so let me consider one case. Here I'll consider 10. Here also I'll consider 10. And then control T, control T. So initially I'm considering 10 and 10. I'll consider one case. Yeah. So now I'll consider instead of 10, I'll consider zero point 0.1. Here instead of 10, I'll consider 0.5. So 0.5 star. And then if I comment this, right, then if I comment this, then what is happening? Then the plots figures that are there, they will not be closed, because if I'm commenting this close all, it means the figures will not be closed. If I uncomment, the figures will be automatically closed. So in this case, if you see, I have reduced the gains. So orange color is the later case, and then blue color is the first case. So the gain I have reduced. So if I put marker to be O, then we'll be able to see. Yeah. So if you see, the phase remains same for both the cases, but the gain I have reduced, so the border plot has come down. So in this way, I can play with zeros and poles to adjust the phase, lag or lead, and also I can use the gain K to adjust the gain. So I can either pull it up or pull it down. Similarly, in the second figure, uh, the gain has come down. So depending upon the gain K value, how much you want to pull it up or down, we can do that. But phase remains same irrespective of the gain, because gain is not having any effect on the phase. But whether the zero comes before or pole comes before, that will decide whether you will have phase lag or lead. And then we can see whatever is the requirement. Based on that, we can decide the zero or pole. So is this clear?
Yes, sir.
Okay. Yeah, so today it is more about understanding the theory and then correlating with the MATLAB. So it is more about understanding what is happening or how the poles are going to affect the closed loop transfer function, or how the zeros are going to affect, understanding the P control, I control, PD control, PI control, PID control, what is lead, what is lag compensation. So it is more about understanding. Once we understand the basics of the control design, now we'll be implementing the controller or designing the control using root locus method in the week 8 as well as frequency method in the week 9. So again, I will be taking one extra class this Saturday where I'll be discussing week 8, and again on Monday I'll take week 9, because 2 weeks I'll be out of station because of my conference. So one additional class I have already taken, other additional class I'll take this week. So to compensate before. Yeah. So just to quickly summarize, in week 7, we have discussed about the basics of the control design. We have started with effect of adding pole as well as zero to the closed loop transfer function. And first we have seen the effect of zero, which will have a derivative effect. So it will fasten the response. Again, if it is far away from the imaginary axis, then it will not have any effect. If we have RHP zero, it will have, why I have written ADC? Okay, adding an RHP, I think I have missed it. So this is adding an RHP 0. So RHP 0 will have a derivative effect, but it will have negative. So it will have a initial dip, and then it will follow. And then we have also discussed about poles. Poles will have an integral effect, so it will slow down. So if the poles are dominant, which means they're closer to the imaginary axis, then it will affect the transient response. Whereas if they are far away, then it will be non-dominant poles and it will not have that much effect on the transient response. So adding a zero will fasten the response. So the rise time will reduce, but that will have a peak overshoot. By adding the poles, we are trying to slow down. So the peak overshoot will reduce. Also, the rise time will increase. Then we have seen how adding the poles to open loop transfer function will affect. So here we have realized by drawing the root locus, we can understand how the closed loop poles move. And then we have seen that in one of the cases, it may become unstable. And for all these cases, we have taken MATLAB simulation case studies and taken different examples to understand the theory. Then we have moved to P control, PD control as well as PID control. And here I have considered one case where the system is open loop unstable, but using proportional control, the maximum we can do is make the system marginally stable because the poles are on the imaginary axis. Whereas using PD control, we can stabilize the system, but we cannot achieve zero steady state error for step response. Whereas using PID control, we can both stabilize the system as well as achieve zero steady state error. And for this also, we have considered the MATLAB simulation case study to get the transfer function and see whether the system is stable or not, the closed loop system. Similarly, you can use the code and check the step response and see whether the steady state error is zero or not. It will be in the third case, it will not be in the second case. Then we have discussed about the lag compensation as well as lead compensation. Basically, lag compensation is kind of PA control, and here the phase will lag. So the pole should come before zero. So the phase will dip before, and then will come back to zero later. And this is how the body plot will look like. Whereas in the case of lead compensation, it is like a PD control and it will have phase lead. So the zero will come before the pole. So the phase will increase before and then it will come back to zero later. And then the plot will look something like this. So this is all about week 7. If you have any queries, you can ask, else we can end this session here. And just an announcement, again, I'll take a extra class on Saturday. So where I'll be discussing about the week 8, which is design using root locus. And again, next Monday, I'll take root locus, frequency domain based design.
Yes, sir.
Any more queries?
No, sir. Thank you.
Okay. Yeah. So with that, I'll end this session. I wish you all the best for your week 7. And if you have any doubts, you can mention in my YouTube video comment section. I will try to respond. Yeah, thanks for
Yes,
making
sir.
this session very interactive. You have been very interactive with
Yes.
the entire session. Thank you so much. With that, I'll end this session and I'll meet you again on Saturday. The announcement will be given by the NPTEL people. Kindly check your email ID. Okay, then I'll end this session. Good night.